Problem Solving and Model Building 2. We're going to be looking now at representation, often via feature engineering and pre-processing, and quite often depending heavily on linear algebra. We also have the spectral theorem, which says if S is an n by n square matrix that's symmetric equal to its transpose, and S is equal to Q times a diagonal matrix times Q transpose, where Q is orthogonal, Q transpose equals Q transpose Q equals the identity. The coefficients of the diagonal are the eigenvalues of S, and these eigenvalues are real numbers. And that leads to the singular value decomposition, which says that if you have a matrix A, which may not be square and in fact is often rectangular, then it can be written as U times this diagonal matrix of singular values, V transpose, where the U and the V are orthogonal, and A transpose A is V times the square of the singular values times V transpose. We often call the diagonal of singular values capital sigma, and the square is capital sigma squared. That is, A equals U sigma V transpose, where A transpose A is V sigma squared V transpose. Equivalently, we often have A equals P V transpose, where P is equal to U sigma. And P, therefore, has to be A V, because V transpose and V transpose V are both the identity. And we also have this relationship, AV equals U sigma. And we can rewrite the singular value decomposition. So if A has rank R, then there are only R non-zero singular values. We can correspondingly partition the U and the V transpose, and therefore we only need the first R columns of U and the first R rows of V transpose and the square matrix of non-zero singular values. We often define P sub R to be U sub R times that square matrix of singular values. And then we get A is P sub R V sub R transpose, where V sub R transpose V sub R is the identity matrix I sub R being the rank of A. Now, we often call V sub R transpose the components of A, and P sub R is the SVD transform, or sometimes called loadings, especially by the statisticians, of A. The terminology is not standard. For example, sometimes we'll say that V sub R transpose is the principal axes of A, and P sub R is the principal components of A. And this is our usage. It's common in mathematics. So we have this theorem. A is equal to P sub R V sub R transpose. V sub R transpose V sub R is the identity. And A transpose A is V sub R sigma squared V sub R transpose, which looks like this in terms of shape. Recall that R is the rank of A, the column rank. And it's also important in matrix norms. For instance, the Frobenius norm is the trace of A transpose A, but that trace is just the sum of the diagonal, and notice that this diagonal matrix we have in the middle is the square root of the singular values, and it turns out that the Frobenius norm is the sum of the squares of the non-zero singular values of A. Now, our focus in this video is on the role of linear algebra in pre-processing, in particular because linear algebra can produce useful representations of the data, especially when such representations lead to dimensionality reduction, which we'll see in a few minutes. So let's review exploration and pre-processing. We have to convert into a numerical array, and often we have to rescale the features. And more sophisticated pre-processing uses matrix algebra quite often. In particular, we often have an old data set that we write as the product of a new representation times a features matrix. And we introduce new variables when we do this, called latent variables. And then our matrix factorization is x equals df, or sometimes called matrix decomposition. For example, in the simulated calculus grades, we had previous is 0 or 1, and the exams range from 40 to 100, so we rescaled. But notice rescaling means we actually were multiplying by a scaling matrix, x equals df. Well, the scaling matrix was just a diagonal matrix with the scaling factors on the diagonal. And we could actually think of our scaling process as multiplying the new data representation by the scaling to get the old one. And often we do what's called low-rank approximation. So dimensionality reduction means we often choose D, the latent variable's dimension, to be much smaller than either M or N, often just 2 or 3. And that means we get an approximation. And the choice of D determines how accurate that approximation is. So for example, let's look at the singular value decomposition and low-rank approximation. So we can divide our U and our V into those corresponding to the first D singular values and those corresponding to the remaining. And we can introduce a new matrix, A sub D, where we have the same U and V with the same subdivisions. We have the same sigma 1 to sigma D singular values, but the remaining singular values have been replaced by the zero matrix. So what that means is when we subtract A minus AD, we actually have U sub R times only those remaining singular values in the lower right diagonal. And that means that our A sub D, our approximate of A, is actually of this form. And our Frobenius norm is just the sum of those remaining singular values. So if they're small, we get a good approximation. In fact, this is known as the Eckert-Young-Mirsky theorem. If A is a M by N matrix with rank R, then the best D strictly less than R approximation of A is given by this U sub D times the singular values we keep times V sub D transpose. And it's best with respect to the order 2 Frobenius matrix norm. The idea behind the proof, if B sub D is any rank D matrix, you can show that the Frobenius norm squared of A minus B sub D is greater or equal to the singular value squared that we throw out, which is the Frobenius squared norm of the difference. We often define P sub D is equal to U sub D times the singular values that we keep. Same shape as U sub D. We define A sub D as P sub D V sub D transpose. And this is what's known as the truncated singular value decomposition. And then we get that the A sub D is of this form and is an approximation of A. So for example, disrupted signals, where a disruption is kind of like an air horn blast or tires of a car squealing as it peels out. So here I have a 50 time series. This is 2 of the signals where the big spikes are the disruptions. This is all of that data in those 50 time series. And so I take that in time series and think of it as a rectangular array. The disruptions, it turns out, are high dimensional. So if this is my A, and then I construct the low dimensional approximation A sub D with rank D equals 3, which gives me this new matrix, which means a new representation for the time series, then here is all the data. Notice that the disruptions, the large spikes, are mostly gone. In fact, here are 2 signals that no longer have the disruptions. These were the original structures of those 2 signals. Disruptions have been removed. Notice that noise in a time series is rarely high dimensional. So this SVD is not a denoising method. It's a way of getting a low rank approximation. And finally, the SVD is also an algorithm. Notice we have our low-rank approximation theorem. It says that A can be approximated by this product of three matrices, and we can define a P sub D, our principal component, so it's approximated by the product of these two matrices. But we can take the first matrix and write it as a set of columns, or a list of columns, and the second matrix is a stack of rows. When we do the calculation, we see that A is now approximately equal to this sum of outer products, P1V1 transpose up to PDVD transpose. This means if A is equal to the matrix with coefficients Aij, then the Aij's are approximated by P1I V1J plus up to PDI VDJ. And that actually means that we can think of the singular value decomposition as this algorithm, minimizing over the P's and V's of the squared difference. This actually is in terms of the squared Frobenius norm of this sum and these Aij's, with the constraint that we have V sub D transpose V sub D is the identity, which is represented by those sums being equal to 1 or 0 respectively. The singular value decomposition is in fact the fundamental theorem of linear algebra, and much of linear algebra is based on the singular value decomposition. Similarly, much of preprocessing and feature engineering and data science is based on the singular value decomposition, and many examples will be given in the associated notebooks. The singular value decomposition is also often modified or rewritten to produce new techniques and representations, such as principal component analysis, which we'll see in the next video.